lecture 22 of our series on numerical methods in civil engineering, we will continue with our discussion of analytical methods for solving the wave equation. We illustrated last time, we talked about the Eigen function approach for solving the wave equation, and we illustrated the use of the Eigen function approach by solving the 1D wave propagation problem in a ring of unit circumference. We solved del 2 phi del t square c square del 2 phi del x square over the domain shown in the figure. So, the shaded region is the ring, and here I am showing that it is of unit circumference. Because of the nature of the geometry, the boundary condition is periodic, that is phi at x is equal to 0, that is if we start from here, if this is our starting point, phi at x is equal to 0 must be equal to phi at x is equal to 1, must be equal to phi at x is equal to 2, and so on and so forth. So, the phi must be periodic. Similarly, the slope of phi, that too must satisfy the periodicity condition. So, phi prime x t must be equal to that x prime phi prime x plus 1 t, and so on and so forth. And we said that to solve this problem, we have to first solve the eigenvalue problem. This is the eigenvalue problem which we solved. We obtained eigen functions of this form, n is equal to e to the power I 2 pi n x, and we said that since the eigen functions are complete, any solution can be expanded as a Fourier series in the eigen functions coefficients phi m, and you can evaluate the coefficients phi n taking into account the fact that we have our boundary, we have initial conditions, right, and if we substitute them in the differential equation, this expansion for phi m, right, if we substitute that in the differential equation, we get and taking into account the fact that my eigen functions are orthonormal, I can get a differential equation in phi n, which we then solved, and finally we got an expression like this. Right, this is where we stopped last time. Substituting this back, this expression for phi n which we got here after solving the initial value problem, we substituted that back in the Fourier series. So, now everything is known, the coefficients are also known, the eigen functions are known. So, we have a complete solution for the wave equation for the ring. Now, if we look at this expression, this solution phi is equal to a n e to the power 2 pi I n x minus c t plus this term. The first function, the first term in the solution is a function of x minus c t, while the second term is a function of x plus c t. Thus, we can write phi as the sum of a function f of x minus c t and g of x plus c t, that is phi is the sum of two parts, one part depends on x minus c t, the other part depends on x plus c t. Each of the functions f and g must be twice differentiable, that is obvious, right, because I have my wave equation involves second derivatives, right. So, f and g must be twice differentiable, and since it is linear, then my equation is linear, they must individually satisfy the wave equation. Both f and g must individually satisfy the wave equation. Let us look at the first part of the solution, f of x minus c t. It is clear that this function will have a constant value wherever x minus c t is a constant, right. If at time t is equal to 0, we consider the point x is equal to 0, and suppose the function f has value f of x 0 at t equal to 0. So, at time t is equal to 0, we are considering the point x is equal to x 0. So, at time t equal to 0, the function f has value f of x 0, right. So, for all times t greater than 0, if x minus x t is equal to x 0, right, then at all locations which are given by x is equal to x 0 plus x t, since x minus x t is equal to x 0, at all locations x is equal to x 0 plus x c t, the function f will have the same value, right. So, what does this mean physically? It means that at least for the first part of the solution, what it means that the same wave translates to the right with a uniform speed of c, right. The information at t is equal to 0, which was f is equal to x 0, at point x 0 on the t is equal to 0 axis, right. If I draw an x t axis at t is equal to 0, at point x 0, whatever the value of f was, right, f of x minus c t was, that is going to get, as time increases, as t goes from 0 to infinity, that information is going to propagate with a constant speed of c, right. So, this is exactly why the equation is called the wave equation, and the parameter c in the equation is known as the wave speed. You can see that what the information, the f of x 0, right, the initial condition, right, the initial solution at f of x 0 is going to move to the right with a speed of c, right, because it is going to be f of x 0 at all points x is equal to x 0 plus c t. So, that means it is moving to the right because x is increasing, right. If I have x, x t, x is increasing, so it is moving to the right, right. It is moving to the right. The information at f of x 0 is getting propagated to the right with the uniform velocity of c. That is why this equation is known as the wave equation. So, let us go back to our solution for phi n t, which we got right there, and we can see that phi n t is of this form, right. If we impose the initial condition phi n at t is equal to 0 is phi n 0 and phi dot n t is equal to 0 phi dot n 0, we get the following conditions for the constants a n and b n. So, we impose the initial conditions to evaluate these constants. We find these constants, we solve those two equations simultaneously, we get our a n and b n of this form. Substituting these values in the Fourier series solution, which was this equation, right, the final Fourier series solution, we get an expression for phi of this nature, right, of this nature, where these are quantities which depend entirely on the initial conditions, right. Recall that from the Fourier series expansion of the initial data, we had phi 0 is equal to, this is how we defined phi 0 n and phi dot 0 n. So, because we did that, the first term in the series is nothing but phi 0 x minus c t, because phi 0 x, look at this, phi 0 x is equal to sigma n to n equal to minus infinity to infinity, phi 0 n e to the power 2 pi n x, right. So, what is the first term? The first term is phi 0 x minus c t, because this is exactly the same except that here I have x minus c t and here I have x, right. So, the first term is phi 0 x minus c t, the second term is phi 0 x plus c t, right. Also, this integral, if we evaluate this integral e to the power 2 pi I n c alpha d alpha, where alpha is an intermediate integration variable, I can show that this is equal to that, right. So, the second term in the Fourier series solution, this term is actually can be expressed in terms of phi dot 0 of at x, and what does it become? It becomes half integral minus t to t phi dot 0 x plus c alpha d alpha. So, we can see we are able to express the entire solution, of this problem, this wave problem in this, in this ring of unit circumference, entire solution in terms of the initial conditions, right, phi 0 and phi dot 0, and finally we can get it in this form after doing this substitution, x plus c alpha is equal to eta, we get it in this form. So, what is interesting about this form? It is clear that it is a function of x minus c t and x plus c t, number 1, that is part of the solution, and moreover the function is the solution is totally dependent on the initial conditions. This last equation is known as D'Alembert formula for the solution of the wave equation. It satisfies both the wave equation as well as the initial condition by construction, right. Although the solution was obtained for the wave equation with periodic boundary conditions, it is clear that the solution does not depend on the boundary condition, right. It depends totally on the initial condition. So, the D'Alembert solution holds for the pure initial value problem without any specified boundary conditions, right. Because you can see here there is no influence of the boundary conditions, there is no influence of the boundary conditions at all. It is totally dependent on the initial conditions. So, we have solved. So, why do you think the boundary conditions are not involved in the solution? Well, it turns out that when we satisfy the initial conditions, we automatically satisfy the boundary conditions, right. For this geometry and for this periodic boundary condition, right, the initial condition, this solution automatically satisfies the boundary condition. So, not only does it satisfy the initial condition, but it also satisfies the boundary condition, but the boundary condition does not appear here because of the nature of the solution, right. It does not, because of the nature of my eigen functions and things like 2 pi I n c t and things like that, because of that it does not really appear in my solution, right. So, the initial condition is such that it automatically satisfies the boundary condition. The initial condition is consistent with the boundary condition. This problem has an, if you have an initial, this is the solution depends only on the initial condition, we find that, right, from our solution, but the initial condition is totally consistent with the boundary condition. So, when it satisfies the initial condition, it also satisfies the boundary condition, right. That is why you do not see the boundary condition explicitly in the solution. So, we have solved the wave equation for a ring shaped domain of unit circumference. We obtained the solution by using the method of eigen functions. Then, by performing suitable variable transformations, we transform the solution to D'Alembert form, which is independent of the boundary condition, right. So, now let us consider a situation where the boundary conditions are not periodic. Well, I said that in this case the boundary conditions do not appear in the solution because the initial conditions automatically satisfy the boundary conditions, right. But now let us consider a situation where the boundary conditions are not periodic. What happens in that case? Is the solution dependent on the boundary conditions? Let us take a look. So, in particular, let us solve the wave equation now over a domain in the one dimensional wave equation. We are going to solve the one dimensional wave equation over a domain 0 to L, x goes from 0 to L, with the boundary conditions that phi of 0 equal to phi of L is equal to 0. So, it is fixed at the two ends, right. The primary variable is 0 at the two ends, and it has the same initial conditions as my previous problem. So, at t is equal to 0, I am giving phi as well as phi dot, right. So, those are my initial conditions which are the same as the wave problem, and in addition I have now non-periodic boundary conditions, which is phi of 0 and phi of L equal to 0. So, again we are going to adopt the eigen function approach. So, we are interested in phi. So, this is my operator Lu, right, Lu, and this must be equal linear operator Lu, and I want to find the eigen values and eigen functions of this operator. So, I solve this problem, right, d2 un dx square, where un are the eigen functions, lambda n are the eigen values, subject to these boundary conditions, which are actually identical to the boundary conditions on phi, because the boundary conditions on phi are homogeneous boundary conditions. If the boundary conditions on phi were non-homogeneous boundary conditions, then the boundary condition for the eigenvalue problem is going to be different, because the eigenvalue problem always must have homogeneous boundary conditions, right. So, since the boundary conditions are homogeneous, the solution does not contain any cosine terms. You can see that, right, because u n at x must be at x, the solution must be equal to 0, right. At x is equal to 0, the solution must be equal to 0. So, it can't contain cosine terms, right. So, it is going to contain sine terms only, and lambda n we can find out after solving the eigenvalue problem, after writing out the characteristic equation like we did last time for my wave equation in a ring. We will find that lambda n is equal to n square pi square by L square. Again, since the eigenfunctions form an orthonormal basis for the function space, I can always represent any solution phi as a sum of these basis functions, of these infinite basis functions, and the coefficient is dependent on time, Cn is dependent on time. So, that is my solution expanded in terms of these basis functions. Now, we note that the sum in this case is from n is equal to 1 to infinity and not from minus infinity to infinity as for the ring problem, because the eigenfunctions are odd in this case, right. We have sine, eigenfunctions involve sines. So, again substitute, we do exactly the same operation that we did for the ring problem, right. Once we obtain our eigenfunctions, we write out our solution in terms of a coefficient and coefficient which is a function of t times the eigenfunction summed over the infinite number of terms in that series, right. Substitute that in my differential equation, substitute that in my wave equation, right, and then from there impose the once I substitute that, I get something like this, right, which is a second order ordinary differential equation in the coefficients Cm. Then I use my orthonormality property of the eigenfunctions, right. I take the inner product with my eigenfunctions, right, and once I do that, I reduce this to this form, right. So, these extra terms go away. So, only the term involving n survives, the coefficient Cn survives. So, I get something like this, right, an equation, a second order ordinary differential equation in Cm, and this is, since it is a second order equation, I need two initial conditions to solve the second order equation in time. I get those initial conditions from my initial conditions of the original problem. So, how do I get the initial conditions? Again, by expanding the initial data which I know, phi at x, phi of x 0 and phi dot of x 0 in terms of the eigenfunctions. Since my eigenfunctions form a basis, I can expand any function in terms of the eigenfunctions. So, I can as well expand phi of x 0 and phi dot of x 0 in terms of the eigenfunctions, right. So, I do that here, and these coefficients again I am going to evaluate using the orthonormality property of my eigenfunctions. So, imposing the initial condition in terms of phi 0 n and phi dot 0 n on the solution of star, which is this, right. We can get an expression for Cn in terms of the initial data. So, we solve this second order differential equation for Cn, impose the initial condition, we get Cn like this, right, Cn as a function of time, that is like this. I substitute that in my series solution for phi. Basically, I substitute, now I know Cn, I substitute that right here, right, I substitute that Cn right here, and I get my phi, which is the final solution, right. This is the final solution. As you can see, this definitely has the boundary conditions explicitly in there, right. It comes from the eigenfunctions, right, it comes from the eigenfunctions, right. So, these boundary conditions you can see at x is equal to 0, x is equal to L, it is going to satisfying the boundary conditions, right. So, now we want to consider the solution for various types of initial conditions. Let us suppose that my initial velocity is 0, right. So, my phi dot 0 is equal to 0, that is one of my initial conditions. So, the second term here drops out, right, the second part of the solution drops out. So, I have phi equal to sigma n is equal to 1 to infinity phi 0 n cos of n pi c t by L sine of n pi x by L. Then using some trigonometric identities, I write cos of sine n pi c t by L sine of n pi x by L in terms of a sum of sines, and if I do that, I get phi is equal to this. You can see why I am trying to do that, because I want to get it in the form where it is a function of x plus c t and x minus c t. So, if the initial displacement, so right now we have only conditions, we have only initial conditions on phi 0, right. We do not have the initial, there is no initial velocity, the initial velocity is identically 0, right. So, suppose I define, since my domain of interest is from 0 to L, and if I define my initial displacement phi 0 x in the interval 0 to L, and if we assume, now this is a big if, right. So, because my domain of interest is from 0 to L, right. So, I am going to give initial conditions only in that region, right. But suppose my initial conditions can be extended along the x axis, right, from x is equal to minus infinity to infinity as a periodic function, so that the so whatever the function I get from x, whatever the shape of the function phi at x is at t is equal to 0 from x is equal to 0 to L, whatever shape it has, I know that at x is equal to 0 and at x is equal to L, it's got to be 0, right, because it has to satisfy the boundary conditions, right. Now, if I extend that, right, I suppose that I assume that my initial condition is extended for the entire x axis, right, stretching from minus infinity to infinity, but extended in such a manner that it satisfies this periodicity boundary condition, right. So, that it is 0 at x is equal to 0, x is equal to minus L, x is equal to minus 2L, x is equal to minus 3L, x is equal to 2L, x is equal to 3L, and so on and so forth, right. If that happens, then the solution is given by this phi of x t is equal to half of phi 0 x plus c t plus half of phi 0 x minus c t. So, basically I can expand this solution for throughout x is equal to minus infinity to infinity in terms of phi of x 0 plus c t, phi of x 0 minus c t. Why can I do that? Well, I can do that because again because my initial conditions are satisfying the boundary conditions. So, my initial condition now is of this form, right. My initial condition is of this form and it is periodic. So, it satisfies the boundary conditions like that, right. So, that is why I can extend it to the entire x axis. I mean, I can extend the solution to the infinite domain. The reason for this is by extending the initial data to the entire domain in the way we showed here, right, in a periodic fashion, we ensure that the pure initial value problem and the boundary value problem have the same solution in the interval 0 x L, right. So, I am extending my initial condition, but I am doing it in such a way that the boundary conditions are also satisfied. This is because the solution of the pure initial value problem ensures that phi x is the pure initial value problem solution given by the D'Alembert formula that ensures that phi at x is equal to 0 and phi at x is equal to L is automatically equal to 0, right. which means that the boundary condition is satisfied. This extension procedure is known as the method of images. Basically it extends, it takes images of the solution, right, images, and extends it, right, images of the, it can be extended to the full problem if phi dot 0 is also extended as a periodic function that is odd at the points x is equal to 0 and x is equal to L. We could extend that because my initial condition, which was only on phi, because I assume that phi dot is equal to 0, phi dot at x at t is equal to 0 is equal to 0. If so, I had my initial condition was only on the displacement, right, and I extended that in a periodic fashion, right, satisfying the boundary condition. If I do the same thing for my velocities phi dot, then I can extend that a full initial value problem, right, where I am prescribing both the displacements, both phi and phi dot. I can also extend that over the infinite domain. So, it can be extended to the full problem if phi dot 0 is also extended as a periodic function that is odd at the points x is equal to 0 and x is equal to L. Similarly, the D'Alembert solution, which is independent of boundary conditions, can be made valid for a finite interval, right, because if we make the D'Alembert solution, if we give initial conditions in such a way that it satisfies the boundary condition, then the D'Alembert solution is, it is just the converse, right, it can, the D'Alembert solution can also be made valid for the finite interval. If both phi 0 x and phi dot 0 x are redefined for minus infinity x to infinity in such a way that they are 2L periodic and odd. Okay. So, this is a point. So, since we are looking at geometry right now, we are looking at how the solution can be extended, right, from a finite domain to an infinite domain, making sure that we take mirror images of the solution of the initial conditions, right. This is a point to look at a very important method for solving partial differential equations, particularly hyperbolic partial differential equations, that is the method of characteristics. The method of characteristics is a very important and very powerful and very revealing method, because it gives a lot of physical insight into the solution of the wave equation, and it is based on geometry and purely based on geometry, right. So, to do that, we look for a geometrical interpretation of the D'Alembert formula, and this helps us in getting at the method of characteristics. So, this is again our D'Alembert solution, phi x 0 x t half of f x minus c t plus f of x plus c t plus this, right. This is my D'Alembert solution. We can see that as in the limit as t goes to 0, phi of x 0 is equal to f of x. Why? Where at t is equal to 0, this part is 2 f x, so that is f of x. This at t is equal to 0, the integration limits go from x to x, so this integration vanishes. So, I am left with phi of x 0 is equal to f of x. Also, if I take the derivative of this solution of the D'Alembert solution with respect to time, I get half minus c f prime x minus c t plus c f prime x plus c t, which at t is equal to 0 is going to cancel out, that is going to give me 0. And if I look at this term, if I take the time derivative, I have to evaluate the derivative of the limits of the integration times the function value here, right, because the integration limits are dependent on time. And if I do that, I get something like this, which is basically g of x plus c t by 2, and since t goes to 0, this is g of x, right. Now, let us consider what are known as characteristic lines as shown in the following figure, right. So, basically I am interested in knowing the solution at some point. This is my x t axis, where x is the distance, right, it is a one dimensional problem, x is the distance in the x direction, t is my time, and I am plotting it like that, and suppose I want to find the solution at time x0 and t0, right. And these lines, these blue lines are what are known as characteristic lines. These blue lines are known as characteristic lines. So, for any point x0, t0 in the xt plane, we construct lines passing through that point with slopes of plus c and minus c respectively. You can see that this line has a slope dx dt is equal to c, right, and this line has a slope, you can see it is passing through x0 t0, x0 minus c t0. So, it has a slope of dx dt is equal to c, and this line has a slope of dx dt equal to minus c. And these characteristic lines have the following equation: x minus x0 by t minus t0 is equal to plus c and minus c, right. So, one of the equations is x minus x0 by t minus t0 is equal to c, the other equation is x minus x0 by t minus t0 is equal to minus c. Let us consider again the first term of the D'Alembert formula, which is this term, a half of f x minus c t. It is clear that at all locations x t along the characteristic lines, f of x minus c t has the same value as it has as at x0 minus c t 0, since along these lines x minus c t is equal to x0 minus c t 0. So, the characteristic lines have the equation x minus x0 by t minus t0 is equal to plus c and minus c. Let us suppose we take plus c, right. Then what is the equation of the characteristic line? X minus c t is equal to x0 minus c t 0, right. X minus c t is equal to x0 minus c t 0, right. So, along these lines, so this is the equation of this line, right. X minus c t is equal to x0 minus c t 0 of this line, right, of this line. So, along this line, by definition, at any point along this line, x minus c t has got to be equal to x0 minus c t 0, right, because that is the equation of that line, right. If that is true, then f of x minus c t has got to be equal to f of x0 minus c t 0, right. So, whatever is the solution at t is equal to 0 and x is equal to x0 minus c t 0 is going to be f of x minus c t is going to have that value, right, at all times along these characteristic lines. So, the initial information here, the initial condition here is going to get all points on this line, for the first term of the solution, that is going to be identical to what it was here, right. If I look at all points on this line, right, all values of x and t which lie on this line, right, at each of these points, the first part of the solution of the wave equation is going to be the same as it was here, right, as it was here. So, f of x minus c t has the same value as it has at x0 minus c t 0, since along these lines x minus c t is equal to x0 minus c t 0. Thus, to find this value of this term in the solution at any point along the characteristic line, we only need to evaluate f of x minus c t at t is equal to 0, right, and when x is equal to x0 minus c t 0. Is that clear? Similarly, the second term of the D'Alembert equation, f of x plus c t, has the same value along the characteristic lines with slope of minus c. So, the second term, right, the second term along these lines, that term at any point on this line, if I look at phi and I look at the part of phi which is given by f of x plus c t, that part of phi is going to be the same here, 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 everywhere, right. That part is going to be the same along this line, while the f of x minus c t, if I look at the first part of the solution of phi, that is going to be the same as here at all points on this line. Thus, at any point along these characteristic lines, the value of the second term of the D'Alembert solution is known if we know the value at the location where this line intersects the t is equal to 0 axis, that is at x 0 plus c t 0, right, at the root, right, where it intersects. Thus, at any point x t, the first two terms of the D'Alembert solution are known entirely from the values of f at t is equal to 0, that is when x is equal to x 0 minus c t 0 and x is equal to c 0 plus t 0. So, at any point, so this is very important, right. What it's saying is that at any point in the x t domain, right, if I know the solution at x 0 minus c t 0 and x 0 plus c t 0, I know the solution, the first part involving f of x minus c t and f of x plus c t is totally known. So, what does this mean? This means if I know the initial conditions, if I know the initial conditions at those two locations on the x axis, I know the final solution at any point, at least the first part of the final solution at any point, right. So, I know the initial conditions at 2 points. So, I know the initial values of f of x 0 minus c t 0 here, that is going to be the same as the first part of the solution of the D'Alembert solution, right. If I know f of x 0 plus c t 0 here, that is going to be the second part of the f of x plus c t term, that part of the D'Alembert solution is known. So, that part of D'Alembert solution is entirely known if I know the value of the function here and the value at the function here, right, f at x minus c x 0 minus c t 0 and f at x 0 plus c t 0. Thus, at any point x t, the first two terms of the D'Alembert solution are known entirely from the values of f at t is equal to 0, that is when x is equal to x 0 minus c t 0 and x is equal to x 0 plus c t 0. So, at any point along the characteristic lines through x 0 t 0, the value of the integral term in the D'Alembert's equation depends on the value of g between x 0 plus c t 0 and x 0 minus c t 0. Why? Let us go back and look at the solution again. You can see what is the solution. It says that this part we already know how to solve. What about this part? This part depends on x minus c t at any point x and t in my x t domain, right. This part depends on the integral, since I know I can write x minus c t as x 0 minus c t 0, because from my equation of the characteristic lines, right. Since I can write x minus c t as x 0 minus c t 0, x plus c t as x 0 plus c t 0, if I integrate along my t is equal to 0 axis between x 0 minus c t 0 and x 0 plus c t 0, between this and this, if I integrate this g s, right, then I know the entire solution, right. So, I know the entire solution. So, at any point depends on the value of g between x 0 plus c t 0 and x 0 minus c t 0. Why? Because x plus c t is equal to x 0 plus c t 0, x minus c t is equal to x 0 minus c t 0. So, the integral in the limits of the integral change from x minus c t to x 0 minus c t 0 and x plus c t to x 0 plus c t 0. Thus, the solution at x 0 t 0 has a domain of dependence on the initial conditions that lies in the interval x 0 minus c t 0 and x 0 plus c t 0 on the t is equal to 0 line. So, it depends. So, the solution here, the solution here depends on the initial conditions, but only on a part of the initial conditions. The solution here does not depend on the initial conditions here, it cannot depend on the initial conditions here. The solution here cannot depend on the initial conditions beyond x 0 plus c t 0. It cannot depend on the initial conditions less than x 0 minus c t 0. So, this is the domain of dependence on the initial conditions, right. So, the solution at x 0 t 0 depends on whatever is the initial condition for the values of x between x 0 minus c t 0. So, if I have some function, right, along for the initial condition I have some function along this axis, right, at t is equal to 0, since its initial condition it must be at t is equal to 0. So, I have some arbitrary function of x, right, for my phi, right, and then I have some arbitrary function of x for my phi dot, right, at t is equal to 0. So, whatever be the arbitrariness here, that is not going to affect the solution here, right. Only whatever the values that lie between x 0 minus c t 0 and x 0 plus c t 0 are going to affect the solution here. So, in fact, all points that in the shaded area in the figure will have a domain of dependence on the initial conditions that is a subset of the interval x 0 minus c t 0 x 0 plus c t 0. So, what I mean is this, so here this point has a domain of dependence between this and this. If I look at a point here, it is also going to have a domain of dependence, but that domain of dependence will be something like this, it will be smaller, right, it will be within this interval, but it will be a sub interval, right. If I have a point here, what will be its domain of dependence on the initial conditions? Well, I draw characteristic lines with slope of minus c and plus c wherever it intersects my t is equal to 0 axis, those 2 points, the region within those 2 points, within those 2 intercepts, that is going to be my domain of dependence. So, the initial values only lying between those 2 points are going to affect the solution at that point, right. So, but it is important to emphasize that the solution at x 0 t 0 may depend not just on the values at the initial line t is equal to 0, but on initial values anywhere inside the shaded region. So, basically what I mean is this, x 0 t 0 I know depends on the initial conditions between here and here, right, x 0 minus t 0 depends on initial conditions here. But then suppose okay, I think we will come to that a little later, but let us go through this first. So, the domain of dependence of x 0 t 0 not only lies on the line t is equal to 0, but encompasses the entire space time domain enclosed by the characteristic lines passing through x 0 t 0. What I want to emphasize is this, I want to emphasize this is that the solution at x 0 t 0 depends on the initial conditions between x 0 minus c t 0 and x 0 plus c t 0, but it is not, it may not exclusively depend on that, right. It can depend on the, if I apply disturbance here at a certain time beyond t is equal to 0. So, my solution, I start my solution from t is equal to 0, right, and I am continuing till infinity. So, at t is equal to 0 I prescribe initial conditions, and those initial conditions are going to affect the solution, I know, right. But then suppose during at some point I have a forcing function, right. I give an impulse, I apply an impulse load, or I somehow excite at a certain point in time and at a certain point in space, I apply an excitation, and that point in time and space is suppose denoted by suppose somewhere here, right. Let us see, somewhere here, right, at a somewhere inside that domain I apply a certain excitation, right. my solution here, my solution at x0 t0 may depend on that excitation as well, right. And how is that going to happen? Let us see. All points that lie in the shaded area in the figure that we looked at will have a domain of dependence, and that we have already seen, right. But the domain of dependence of x0 t0 not only lies on the line t is equal to 0, but encompasses the entire space time domain enclosed by the characteristic lines passing through x0 t0. Suppose that for a particular problem I have quiescent initial conditions. What does quiescent initial condition means? That I do not give any initial displacement, any initial velocity, right. F and g are both 0 for all points lying for all points lying between x0 plus minus ct0 and x0 plus ct0, right. So, basically I am saying that along this line my initial condition says phi is equal to 0 at time t is equal to 0, phi is equal to 0, phi dot is equal to 0. Initial condition says there is absolutely 0 displacement, 0 velocity. Does it mean that the solution here will be 0 for all time? Well, not necessarily. That is what I am trying to get at. It may not mean just because the initial condition at time t is equal to 0, its domain of dependence along the line t is equal to 0 shows that everything, there is no excitation at all, right, no displacement, no velocity. Does it mean that the solution here will be 0 for all time? Well, not really, right. Why? Suppose at a subsequent time t1 which is greater than 0 but less than t0, right, a disturbance occurs at a point in the shaded region, say a point marked in red in the figure. So, basically suppose at time t which is greater than 0, because I am moving along the time axis, right. So, that is after I commence my solution, right, after I commence my solution I have an excitation here at this red point, right. I apply an excitation here. In that case, the disturbance is going to propagate out from this point along the characteristic lines passing through this point, right. So, since I apply disturbance here from this point along the characteristic lines passing through this point with slope c and minus c, this is going to move out, right. This is going to move out, and then it goes and reaches these blue points, right. So, when that information reaches points marked in blue on the characteristic lines through x0 t0, it will influence the solution at that point, right. So, once this disturbance propagates to here, right, these points, it is going to influence the solution here, right. And if the time, and it may subsequently affect the solution at x0 t0, provided that the time taken to traverse the entire path shown in yellow is less than t0. Let us look at it again. So, I have a disturbance here which is occurring at time t1, right. This disturbance is going to propagate along the characteristic lines with slope minus c and c, right, and it is going to, suppose it reaches these points, right, which in turn lie on the characteristic lines of x0 t0, right. So, if this solution reaches here, right, if this propagates it, if this influences the solution here, that is again going to propagate from here along the characteristic lines, right, and it may actually affect the solution at x0 t0 provided the time it takes for that disturbance to travel from here through here through here and from here through here through here is less than t0, right, because we are interested in the solution at time t0. So, if the disturbance takes a longer time to reach that, then it is not going to affect, right. even though it might have occurred, this disturbance might have occurred at a time t1 which is less than t0. It might have occurred at an earlier time than the time of interest, but it is not going to affect the solution at the time of interest t0 if the path along the characteristic lines to reach that point is longer than it can travel with the wave speed c. Is that clear? So, when that information reaches points marked in blue, it will influence the solution at that point and hence may subsequently affect the solution at x 0 t 0, provided that the time taken to traverse the entire path shown in yellow is less than t 0. The notion of domain of dependence is explained best with reference to sound waves. The domain of dependence originates in the fact that at any point in time at a spatial location, I can only receive signals from sound waves that were generated at a previous point in time. So, I have a point in time and space, I can only receive signals from signals which were generated at a previous time, right. Also, the time between the generation of those waves and the current time must be sufficient to allow the sound waves to traverse the spatial distance between the source and the point at which I am interested, right. So, not only must it occur at a previous time, which is the second point here, right. Not only must it occur at a previous time, but the time it takes for the sound wave to travel must from the source to my point of interest where I am observing the solution must be less than the time at which I am observing the solution, right, than the time at which I am observing the solution. So, similar to the domain of dependence, points on the initial line, say t is equal to 0, have a domain of influence comprising the part of the space time domain where the solution is affected by the value of f and g at the point. So, this is the domain of dependence, this is the domain of dependence of x 0 t 0. Similarly, for points on the t is equal to 0 line, I have what is known as a domain of influence, right. This is the domain of influence of, so whatever be the initial condition at x 0, it can only affect this part of my space time domain that is shown in the shaded region. It is not going to affect any part outside this region, right. So, this is the domain of influence, and the domain of influence is limited by the fact that a wave generated at some time at a point cannot influence events at another point in less time than it takes to travel the distance between those points, right. So, that is my domain of dependence. I have a point in x t, right, not on the t is equal to 0 axis, at some point in the course of the solution, right, and the future, right, not in the initial time, right, and I am interested in what part of the space time domain can influence my solution there, right. So, that is giving me my domain of influence. Then I have the domain of dependence, sorry, that gives me my domain of dependence, and then I have my domain of influence, which tells me that I have a point on the t is equal to 0 axis. What are the possible space time configurations that the initial condition at that point can ever affect, right. So, the total domain of influence. Okay, we will continue our discussion of the method of characteristics next class, and then we will try to move on to analytical techniques for the solution of parabolic and hyperbolic equations, but they are as I said last class, some of them are very common to those for the method of Eigen functions can be used over all these classes of all three types of canonical partial differential equations. So, it will probably be a little repetitive, but I think it might be worth going through. Thank you.